4.6, graphing with calculus and technology. Okay, so here it says produce graphs of this function here that reveal all the important aspects of the graph. So we want to find intervals of increase, intervals of decrease, inflection points, and intervals where the function is concave up, intervals where the function is concave down. Okay, so what I'm going to do is first I'm going to take the derivative, because the derivative tells you where it's going to be increasing. So that's where the derivative is positive, and it's decreasing where the derivative is negative. Okay, and then so the derivative is, okay, the derivative of sine is cosine, so it's 9 cosine x. And the derivative of cotangent is negative cosecant squared of x. Okay, and then I'm also going to take the second derivative, because that's inflection points and concave up and concave down. So concave up is where the second derivative is positive. Concave down is where the second derivative is negative. Okay. Okay, so the second derivative, of course, is the derivative of the first derivative. So the derivative of cosine is negative sine, so that's negative 9 sine x. Okay, now this part right here, this is cosecant of x squared. So the square is this is the outer function. The square is the outer function. Okay, so 2 cosecant x. So the derivative of cosecant squared is you bring the 2 down, and then you reduce this by 1 power. So this reduces to a 1, like right there. And then you multiply by the derivative of the cosecant, which is the negative cotangent cosecant x. Okay, this is the derivative of cosecant x. Okay, the inner function. Okay, so here, let me just make a note. X squared is the outer function. Okay, so that's 2x, and then okay, so now, in just simplifying, we're going to get negative sine x plus 2. In case you have a cosecant x and a cosecant x here. So that's cosecant squared of x times cotangent of x. Okay, so what I'm going to do is I'm going to graph this one, the original function, and this one, the derivative, and the second derivative. Okay. I'll tell you what, I'll graph these two first, and we'll answer these questions here. Then we'll graph this third one and answer these questions. Okay, so let's go ahead and do that. Okay, so I'm going to switch over to Geogebra. That's at geogebra.org. Okay, so here's geogebra.org. Start the calculator. Okay, I'm going to put in the first function, which was 9 sine of x plus the cotangent of x. Okay, so that's the original function right here. It's like kind of weird looking. And you can actually get some of the stuff from the original function, but it's much easier if we just calculate the derivative. Okay, if we just graph the derivative, so 9 cosine x minus the cosecant squared of x. Okay, so the derivative is this blue function here. Okay, so the original one is green, the derivative is blue. Okay, now the question was on the interval from negative pi to pi. So that is basically from about -3 for from about -3 to 3.14 to 3.14 to positive 3.14. So we're looking about at just this interval right here. Okay, now the derivative is, the first derivative is this blue function, okay? So the blue function is negative between negative pi and this approximately negative 1.458, okay? So this, the derivative is negative there from negative pi to negative 1.458 or negative 1.46. It's positive, see the derivative is above the x-axis. So that means it's positive from negative 1.46 to negative 0.35. It's also positive from positive 0.35 up to positive 1.46. So this interval and this interval are going to be where it is concave, where it's increasing, where the function is increasing. The function is decreasing from negative pi to negative 1.46. It's also decreasing from negative 0.35 to positive 0.35, and it's also decreasing from 1.46 to pi. Okay, so hopefully that you understood that well. So I'm going to go back. I'm going to go back to input those answers in. So again, it was increasing from approximately negative 1.46 up to negative 0.35. Okay, that's where the first derivative was below the x-axis, and then from 0.35 up to 1.46, it was decreasing there. And then it was, it was increasing here. It was decreasing everywhere else, which would be from negative pi to negative 1.46. And then from negative 0.35 to positive 0.35. And then from 1.46 to pi. Okay, so that's where it was decreasing, those three intervals there. Okay, now I'm going to go ahead and plot the second derivative. Where it crosses the x-axis, those will be inflection points. And where it's above the x-axis, they'll be concave up, and where the second derivative is below the x-axis, that will be where it's concave down. Okay, so let's go ahead and let's go back over to the graph here. I'm going to graph the third function, which is the second derivative. That's negative 9 sine x plus 2 cosecant squared of x times cotangent of x. Okay, so the red function is the second derivative, okay? Now, I can zoom out and kind of see what's going on. So this red function definitely is above, hold on a second. The pi is about, it looks like it has an asymptote right at pi. Yeah, it looks like it has a vertical asymptote at pi. But it's above the axis right here until it gets to here, and then it's below. And then it looks like it also has another asymptote at pi and negative pi and pi. Okay. So they want us to find the inflection point. Well, the x value is going to be approximately negative 0.6976. So to find the y value, I'm going to go f of, wait, what was that value? Negative 0.6976. Okay, so the y value is negative 6.974. Okay, so now if we round this off, we get negative 0.7 and comma negative 6.97. Okay, that will be an inflection point. Another inflection point will happen here. What is this? Oh, it's not. Dang, it's not. What the? Okay, it's not picking the point up for me, but I know that it's the. I know that it's the other one. So I'm gonna go f of positive 0.6976. And that's 6.97. Okay, so these 2 points, negative 0.6976. So this is going to round off to negative 0.70, comma negative 6.97, and then negative 0.70, comma positive 6.97. Those two are going to be the they're going to be the inflection points. Okay, so I'll go back over to here and put those answers in. Okay, so they already have the parentheses, so I don't need that. Okay, so negative 0.70, comma, negative 6.97, and then positive 0.70, comma, positive 6.97. Okay, so those answers should work. And then this negative 0.7 and the positive 0.7 is also where you're going to have cutoffs between the things. So let's go back over really quickly and look at the graph. Okay, so between negative pi and negative 0.7, it's concave up because the second derivative is above the x-axis. From negative 0.70 to positive 0.70, it's going to be, wait a minute. Okay, so hold on. It looks like there's an asymptote at 0. So from negative 0.70 to 0, it's concave down. From 0 to positive 0.70, it's concave up because it's up here, because the second derivative is above the axis. And then from 0.70 to pi, it's concave down. Okay, so we'll go ahead and put that information in to here. Okay, so from negative pi, wait, it says round to 2 decimal places. Let's do that with the pi also. So pi is approximately 3.14 to negative 0.7 or 0.70. And then we also found that from 0 to 0.7, it was above because there's an asymptote at 0, so it kind of flipped up to being above. Okay, and then just the opposite of that right here, so negative 0.7 to 0, union 0.7 to 3.14 to positive 3.14. Okay, so that should get you the answers. Okay, any questions about that? Okay, let's go to the next exercise. Same sort of thing. Intervals of increase and decrease, inflection points, and intervals where the function is concave up and concave down. But we have a different function. Okay, so here we have this rational function. Okay, so let's go ahead and okay, so there's the original function. Let's go ahead and calculate the derivatives. So the first derivative let's use the quotient rule. So low to high. So that would be this one times the derivative of that. The derivative of that's just 1. So it's just going to be this. Times 1. So low d high. Minus high, which is x d low. So the derivative of this bottom part is 3x squared plus 2x plus 0. Derivative of 9 is 0. Okay, over the square of the denominator. Like that. Okay, so that's x cubed plus x squared plus 9 minus 3x cubed minus 2x squared. Okay, all over nothing squared. Okay, so it is, we end up with, okay, x cubed minus 3x cubed is negative 2x cubed. And then x squared minus 2x squared is minus x squared. And then plus 9. And that's all over x cubed plus x squared plus 9 squared. Okay, so this is the thing. I forgot to write that down. Let me just write that down really quickly. Oh, I got it here. Okay, here we go. Okay, so I'm going to go over to Geogebra, and let me just start over. Okay, so start the calculator. And I'm going to put in, first of all, the original function, which was x over x to the third plus x squared plus 9. Okay, so there's the original function. And I'm also going to put in the derivative, the first derivative, the negative 2x cubed minus x squared plus 9x, wait. Is that just a 9 there? I'll double check in a second. Wait a minute. What the? Okay, now put the denominator in. X cubed plus x squared plus 9 all squared. Okay, so just a second. Let me check. Okay, good. Okay, so the original function is in green, and the first derivative is in blue. Okay, so we're looking where it's increasing and decreasing. Now it does appear that the green function is what we're after, the green one. No, I'm sorry, the blue one. The blue one is the first derivative, so that determines where it's increasing and decreasing. So as long as the blue one is above the x-axis, and it looks like it is everywhere. Yeah, there's no dots here. So it looks like it's above the x-axis from negative infinity. And then it has a vertical asymptote here. Oh dear. Okay, it looks like a vertical asymptote right here. We'll have to figure that out. So it's increasing from negative infinity up to whatever that vertical asymptote is, and then from that vertical asymptote up until it crosses the axis right here, up until 1.5. So it's increasing from negative infinity to the vertical asymptote, and then from the vertical asymptote up to 1.5, where it's below the axis, and then from 1.5 to infinity, it's going to be increasing. Okay, from 1.5 to infinity, it'll be increasing. Okay, So two intervals where it's increasing, I'm sorry. From 1.5 to infinity, it's going to be decreasing. I'm sorry. Okay, so hopefully that was a good explanation. Let's go back. We need to find what that vertical asymptote is. And that's going to be where the denominator is 0. So we'll have to take this denominator here. Actually, you know what? It's going to be easier if we just, since we're using since we're using that anyways, let's just put that in there. X to the third plus x squared plus 9. And see where that's 0. Okay, that's 0 right here at negative 2.47. Okay, so negative 2.47 is the cutoff point. Okay, so in summary, increasing from negative infinity to negative 2.47. Increasing from negative 2.47 up to 1.5. And then decreasing from 1.5 to infinity. Okay, so we'll go ahead and put those answers in. Okay, so increasing from negative infinity up to the vertical asymptote. And then from the vertical asymptote up to 1.5. And then decreasing from 1.5 to infinity. Okay, now, it's really nasty to take the derivative of this. Okay, so let's do a different route this time to determine concave up and concave down. So what we're going to do is concave up, that'll be where the first derivative is increasing. And concave down, that will be where the first derivative is decreasing. Okay, and we can see that information from the graph. So just keep in mind, concave up is where the first derivative is decreasing. Concave down will be where it's decreasing. Points of inflection will be points on the graph where what those are going to show up as will be local minimums and maximums. Of the first derivative. Okay, that's what points of inflection are going to be. Okay, so let's identify the points of inflection first. So we're focused on this blue graph, which is the first derivative. Okay. Now, here, what happens? GeoGebra is really nice because they give us the extremums. So it's coming. The graph is coming down. The blue graph's coming down. It comes down to there. Then it actually goes up slightly, and then it goes back down. And this is just where they intersect. Okay, so this right here, if you take that value there, this is the x value of a inflection point. Okay, so let me negative 0.4988. We'll do that one. So we're going to go f of negative 0.4988. Okay, these are the coordinates of an inflection point. These are the coordinates of another one, 0, 0. Okay, if you put a 0 into the function f, you get 0. So 0, 0 is also in there. Just remember that. And then this is where they intersect. That's nothing. This is where it intersects the x-axis. Then here's another extremum. Okay, so 2.456. Okay, 2.456. So f of 2.456. Okay, so we have inflection point negative 0.5, comma negative 0.005. 0, 0 was another one right here. So there's that one, but with these coordinates though. So 0, 0, and then the third one was approximately 2.46, comma 0.082. Okay. There's a second here. Okay, so I'm going to go back to the other page and write those down because I can't write it here, unfortunately. Okay, so the first one was negative 0.5 approximately, comma negative 0.05. The second one was 0, 0. And the third one was 2.46, comma 0.082. Okay. Okay, so yeah, so those 3 points there. Okay, I come back to here. Now we're going to find out where it's concave up and down. Okay, so it'll be concave because the graph is increasing. The blue one's increasing from negative infinity up to approximately negative 2.47. It's increasing. That's concave up there. Concave down here. The function, this is a local minimum. So it's concave down from this asymptote, negative 2.47, up until negative 0.5. And then from negative 0.5 to 0, it's concave up. And then from 0 to this 2.45, it's concave down. And then from 2.45 or 2.46, I'm sorry, up to infinity, it's concave up. Okay, so concave down, concave up would be from negative infinity up to negative 2.47, and from negative 0.5 up until 0, and from 2.46 to infinity, and then concave down will be the other ones. Okay, so let me go ahead and write that down. Okay, so concave up we determined was from negative infinity up to negative 2.47. That's where we have the asymptote. And then from negative 0.5 to 0. And then from 2.46 to infinity. And then concave down was from negative 2.47 to negative 0.5. So just like from there to there, and then from 0 to that one, 0 to 2.46.